Okay. Welcome, everybody. We're happy and proud to have with us today Larry Samuelson from Yale, who needs our introduction, yet we shall introduce him all the same. An expert in repeated games, evolutionary game theory. He wrote 6 books. He was in the editorial, or is on the editorial board of basically any journal you can think about. And he will talk to us today about something that has to do with information. So very interesting. Stage is yours.
Thank you. I'm pleased to see so many old and some new friends. It's not quite as nice as being in the same room, but I'm really happy to be here. This is a paper with Jakob Steiner. It's a follow-up on a previous work that we did together with Art Robson. And it's a paper about growth. This is a game theory seminar, so I'll make the case a few slides in that there really is a sense that we can think about this in terms of game theory. The aspect of growth that we're interested in is that stochastic growth involves the multiplication of random variables. Models like that show up in many places. In economics, the interpretation we're going to initially adopt, we can think of wealth accumulation as the product of random returns. In statistics, we can think of the growth of a sample likelihood as the sample size expands, and that's the product of the likelihoods of the observations. In biology, we can think of the population size as being the product of random growth factors. In each case, we're going to be interested in a growth maximizing policy. We're going to look at an abstract model that we will argue captures the essential features of these various settings, and we're going to characterize optimal growth policies. To do this, we're going to introduce a notion of merit. We'll have to interpret that word rather generously, but a notion of merit that describes the contributions of the various individuals to the growth process. And our basic result is going to be that the optimal growth policy satisfies a consistency condition between the shares of, in the economic context, aggregate wealth and the merits of the individuals. So in economics, this is going to be consistency between wealth shares and merit shares. In statistics, a particular application that I've learned some people at least call predictive coding. This is going to be a consistency between the predictive and the sensory elements of the predictive coding scheme. We're going to need some tools to do this. The basic observation is that when we're talking about products of random variables, large deviations become relevant. Large deviations are exponentially rare, but large deviations can have exponentially large effects on the growth process. And so we have to balance those two features. The natural tool that comes to hand for doing that is the notion of a Kullback-Leibler divergence, because that helps us describe the likelihood of these large deviations. And we're going to get some mileage out of applying results for the divergence that are usually confined to probability distributions a bit outside that purview. We're going to refer to what we'll call a generalized distribution. You can think of this as just a probability distribution that someone forgot to normalize, so it doesn't necessarily add or integrate to one. We're going to show that lots of things we know about divergence for probability distribution hold more generally, and we're going to use that. A very brief comment on the literature, brief enough that I'll actually mention almost no names. In economics, there's an enormous literature, sometimes called the new growth theory, about the relationship between inequality and redistribution and growth. And our comparison between wealth shares and merit is going to allow us to have something to say in our rather abstract setting about that. In information theory, there's a longstanding principle called the Kelly betting rule or the Kelly investment rule. That's going to show up very quickly as a special case of what we do. And the predictive coding models typically use variational methods to establish their results. And we're going to get an alternate route to that based on our growth ideas. That's the end of my introduction. Presumably not enough detail there for anyone to really ask about it, but if before we go to the model, you have questions of motivation or interpretation or other, I'm happy to take them. Now, in general, once I've given you a little more basis for it, I encourage you to ask questions as we go along. So let's try to make some of this precise. First thing I'm going to do is acquire some notation. The top series on this page is the usual sort of notation we have for probabilities. You can think of this. I'm hoping you can see my cursor on the screen. You can think of that, thank you, as a joint probability distribution. And from that joint probability distribution, we can think of having marginals on either dimension, and we can think of having conditional probability distributions, again, in either way. And these things are related in the usual ways that we expect them to. When we start talking about wealth accumulation, which is going to be our first interpretation of our growth model, this we will think of as a distribution of wealth shares amongst the members of the economy. We will think of this as a conditional distribution describing the returns that these members receive, and we can put them together to get this joint distribution. The joint distribution is going to turn out to be the only thing that matters for the growth process, and so we could think of that as our primitive. The reason I start by introducing probabilities and likelihoods is, of course, because the joint distribution doesn't uniquely identify the probabilities and likelihoods. And so it helps to keep track of both of those. Now, in this bottom system here just reproduces the same set of ideas, except now I no longer want to think of these likelihoods as being a probability distribution. I just want to think of this as a function, and a non-negative function. That's why I suggest you can think of this as a conditional probability distribution that someone forgot to normalize. And so I'm going to start from this marginal distribution. We don't have to, but I will always take that to actually be a distribution. That's all we'll ever need. And this generalized likelihood or function, and then together from those, we can construct once again something that looks like the joint distribution, and we can construct something that looks like the other marginal. Those two are not necessarily going to be probability distributions. We can look at the other likelihood. That one will turn out to be a probability distribution. And it helps to keep track of which things are necessarily probability distributions and which ones are not. And so our convention hereafter is going to be, if it's something we know is a probability distribution, it gets a bold letter, and otherwise it gets an ordinary letter. So that's some notation to keep in mind. Now let's look at the growth process. To make this more concrete, I will interpret this for most of the talk in terms of wealth accumulation. I'm going to have a finite set of people. You're going to have a finite set of states, and there are going to be discrete time periods. You can think of a planner, and this planner chooses policy. And what is a policy? We think of this economy starting with a lump of wealth that I'll think of as being of size 1. And over time, the wealth owned by various individuals is going to grow or shrink. And I'm going to allow my planner, my planner, at the beginning of every period to choose an allocation. And what this allocation does is scoop up all the wealth in the economy and then divide it up amongst the agents. Or equivalently, this allocation redistributes the existing wealth in the economy between the various agents. And Q of I just describes the share that agent I receives. A state is drawn, IID, in each period according to this prior distribution. And then this function describes the return on wealth of individual I in the state that is drawn in period T. The planner chooses this policy to maximize the long-run growth rate. So the planner chooses a policy from a set of feasible policies, and the long-run growth rate we can represent in various ways. It's in each case an expectation over the states of the log of the aggregate return in the economy in the various states. And so this aggregate return, I can sum over individuals how much of the wealth each one had and the return they received, or I can compose this into the joint distribution, or I can look at the marginal distribution over states. And this set of constraints, depending on the setting, might capture various factors. In the statistical setting, this might represent a set of plausible models that the learner is considering. In the biological setting, this might capture the biological feasibility of various genotypes. If we're talking about literally wealth accumulation, this might, of an individual, this might capture constraints on the portfolio that they're allowed to adopt. In an economy, there may be constraints on how unequal the planner can make the distribution of income.
May I ask a question now, or shall I?
Yeah, do please, because that's our basic economy, please.
Yeah, so my question is indeed about understanding the model. So you say that the time invariant allocation is basically decided by the planner, and that is the share of the wealth that is given to to each player at each time.
Yes.
But the non-bold, the italic probably Q, that is something I don't really understand, and also the omega of T.
So
perhaps elaborate on that.
So I want you to think of this as a description of the technology available to the agents. And so you think of we being the members of this economy, and each of us has a startup that we're convinced is the greatest investment, and whatever wealth the planner allocates to us, we put into this startup. And this describes the fate of our startup. So each of us has a different one, so that's why it depends on I. And this is a common state of the world, but it can have an idiosyncratic effect on the return that each of us owns.
Ah, okay. And that effect can depend on time.
The function itself does not depend on time. What depends on time is the value of the state that is drawn.
Mm-hmm. Okay. Then my last question is, why, so practically, how can this policy be implemented? It seems like there is someone who basically is empowered to divide whatever is gained, or to redistribute that arbitrarily, or is that not the case?
So practically is not a word that's going to come up often in this talk. But yes, think of this as a planner who has the power to, at the beginning of every period, redistribute arbitrarily.
Okay, thanks.
Now, here's an example where this actually might make sense. Let there be, again, a collection of states distributed according to some prior. Let the returns be specified like this. There is some candidate return, and for each individual, if the state matches the name of that individual, the individual earns that return, and otherwise the wealth owned by that individual disappears. And there are no constraints on the allocation. You can arrange the allocation across the individuals however you want. What is this? This is essentially a model of a horse race where each of us bets on a different horse. Or equivalently, this is a model of asset allocation where we think of the individuals as assets. And I've adopted a particularly simple asset return rule. In each period, one asset pays off and all the others fail. That's the equivalent of only one horse can win the race. Then it's well known that the optimal allocation in that case matches the prior distribution over the asset, over the probabilities that each asset is the one that's chosen. This is what's commonly called the Kelly investment rule, or the Kelly betting rule. And so this is a simple model of optimal portfolio construction. I could allow the R's to vary across assets. I could allow a little more complicated asset return, and that would give us a more complicated rule here, but the same kind of principle would hold. And so in that case, in this case, the planner who has the ability to redistribute the wealth is you, when every period you look at your portfolio and decide to rebalance. And there are various things you could do. There might be one asset that is more likely to be a success than the others. One thing you could do is put all of your wealth into that asset. It turns out that would not be a great idea to do, but you could. And if you want to maximize the growth rate of your portfolio, the proportion of your wealth that goes into each asset is the probability that that asset is the one that pays off. So if you want, think of that application throughout, then that will help you interpret things. Now, one thing that you might have asked is, why have I restricted the planner to stationary portfolios? I require that there be this allocation of the asset across individuals, and it be the same in every period. Now, perhaps it's obvious that that's general enough because the states are drawn IID, but perhaps not. You might also ask, why is growth rate maximization the appropriate objective? Why not something else? Indeed, one criticism of Kelly's rule was that we should be looking at expected utility maximization instead of growth rate maximization. Here is a result. This is a familiar result from information theory that gives us some cover for both the stationarity and the growth rate maximization. And roughly what this result says is you can take any history-dependent policy, any policy that maps from a history of realizations of the random variables, and indeed the history of the past allocations that you have made, into a current allocation. And you can compare that to the optimal stationary policy. And with probability 1, the optimal stationary policy does at least as well, and in general overwhelms any other policy. And so that gives us some warrant for looking at the objective that we do. This top equation here is a straightforward calculation. It tells us that in any period in which the outcome of the random variable is omega, the share of the aggregate wealth in that period that came from person I is given by this distribution. To obtain that, we ask, how much wealth did I start with? What was the return on that wealth? What was the total return in the economy? And that gives us a share of I's wealth. Now I'm going to define a distribution called the merit distribution. And what this does is identify the share expected over states of aggregate wealth produced by person I. And so my notation for the merit distribution is M for merit, I because we're talking about person I, Q because this is determined by the policy that is chosen by the planner. And this is the expectation over states of the share of person I. Now, 2 comments about this. There are other shares of aggregate wealth that you could think of choosing. We've taken shares first and then aggregated over states. One thing you could have done is aggregate over states first and then take shares. And you can imagine some other things that you could do. Why do we do this? Well, this is the one that works, is the best answer I have to that. And the other is that merit is maybe not our favorite name because it has this kind of normative feeling to it. And we will interpret the merit distribution as describing the relative importance of the individuals in contributing to the growth of wealth. But this merit distribution it depends on the policy that's chosen by the planner, and as a result can be relatively arbitrary. For example, let's suppose the planner decided to give all of the wealth to a single person. Then you work through this distribution, you'll get what in hindsight is an obvious and trivial answer. The person who gets all the wealth has merit 1 because they're responsible for all the wealth accumulation, and everyone else has merit 0 because they're responsible for none of it. So that describes reasonably appropriately the share of wealth accumulation that that person is responsible for, but it's hard to find any normative interpretation there. And indeed, that might be a very silly thing for the planner to do. So we have to be a little careful about interpreting this word merit. And just a comment, it's not too hard to see that, but for extraordinary circumstances, the merit distribution is not going to be the same as the initial allocation. Indeed, as long as there's differences in the technology the agents have access to, these are not going to be the same. Now, just a reminder first of what the Kullback-Leibler divergence is. I call it a pseudo distance because it doesn't satisfy the symmetry that we would really like a distance to satisfy, but it's typically interpreted as a measure of how far apart 2 probability distributions are. And so if we have probability distance P and Q, this is the calculation of this distance. And our basic result is that the optimal policy minimizes the distance or the Kullback-Leibler divergence between the policy and its induced merit. So we're going to interpret this, we're going to establish this, but first, just to understand it, we look over the set of feasible policies. And a policy is optimal if we can calculate the induced merit distribution and then ask, fixing that merit distribution, if we looked for the policy closest to that merit distribution, and we find that that minimization problem is solved by the candidate optimal policy we started with, then we can conclude that is indeed the candidate optimal policy. I've been a little imprecise in that. This is in fact a necessary condition, and I will describe later, if time, the additional thinking we need to do to make this necessary and sufficient. If this is an interior policy, then it's immediate that it's necessary and sufficient. And the difference between necessity and sufficiency is that we have to worry about excluded people or corner solutions. And so we can think of this, we won't go too astray, as both necessary and sufficient. We call this the merit principle. It's, in a sense, a naive merit principle. What do I mean by saying it's a naive merit principle? This is not an exercise in minimizing the difference between the policy and the induced merit distribution. Instead, it fixes a candidate optimal policy, identifies its merit, and then holds that merit fixed, and then looks for the closest policy. In general, you could reduce this distance if you jointly optimize over both the merit distribution and the policy, subject to the constraint that the policy in question induce that merit distribution. But the result of that problem would not be the optimal growth policy. Let me illustrate with an example. To make this all the clearer, in this example, there's going to be no uncertainty at all. There's just a single state. I'm going to have 5 people. And so each person is going to be characterized by a single return. And it's going to be easy. Individual I has return I. So person 1 has an investment project or a startup that returns 1. Person 2 returns 2. Person 3 returns 3. 4 returns 4, and 5 returns 5. I'm going to not allow policies to be arbitrarily chosen. There is going to be a constraint on the optimal policy. That constraint is going to be, it cannot be too unequal. And indeed, that constraint is going to be that the entropy of the policy has to be at least 1. Now, the policy that maximizes growth, I mean, agent 5 has the highest return, and so a really naive view would be that you would give all of the wealth to agent 5. That's a bad idea. Excuse me. If we were unconstrained, that would be a wonderful idea, because there's no uncertainty here. In the presence of uncertainty, it's generally not a good idea to give all the wealth to the person who has the highest return. That gives you an insufficient amount of diversification. In this case, that would be a good idea. The wealth constraint precludes us from doing that. And so the optimal policy, the inequality constraint precludes us from doing that. And the optimal policy that satisfies the inequality constraint looks like this. Agent 5 still gets the vast bulk of it. And then we go down the line, giving less and less to the less productive agents, but giving each of them something in order to satisfy this constraint. Now, here's the induced merit for each of these. Under that policy, agent 5 has the highest merit, contributes the most to the aggregate wealth share. 4 has less, 3 less, 2 less, and 1 less than that. The sensible thing to do is to compare these two pictures. So who they are together, the blue dots are the optimal policy, the red dots are the induced merit. And so this optimal policy satisfies the condition that I can fix the optimal policy, calculate the induced merits, that gives me the red dots, and then I can ask, given those induced merits amongst the feasible policies, which one comes closest in the sense of Kullback-Leibler divergence, and it is indeed this blue one. This is an interior policy, right, sort of on the margin for agent one here, almost to zero, but that's actually interior. And so in this case, this is a necessary and sufficient condition for this to be an optimal growth policy. If I were to remove the constraint that I hold the merit fixed while finding the policy that is closest to the merit, if I were to allow both of them to vary while still respecting my inequality constraint, I would get a case where the merit distribution and the minimizing distance policy are still different from one another, are closer to one another than in this graph, but the policy would induce a lower growth rate. If I were to eliminate the inequality constraint on policies, if I were to allow any policy, then the optimal policy would give all of the resource to person 5 the optimal policy, and the induced merit would be identical in that case. And that's a general result. If there are no constraints on the allocation, then the merit induced by the optimal policy is the policy itself. This is just the statement that if you put a distribution down in the Kullback-Leibler divergence and ask what's closest to it, the answer is itself. And so if I put down a candidate merit and have no constraints on the distribution and ask find the closest distribution, I'm just going to get that merit back. A good time to pause for clarifying questions on this result.
Larry, I think I have one, if I may. However, it's not on this example. I would like you to comment on what happens in the previous example, the one where the Q of omega and I is equal to the indicator of omega equal to I. Yeah, that example. So would it be true here that Q is the same as MQ?
Yes, it would. And it would, because in this case, I've placed no constraints on the allocation at all. And so in this case, I would ask you to fix a candidate allocation, and you would say, well, I've got a good idea. How about if I set the allocation equal to the probabilities? And then I would say, okay, I want you to calculate the merit. And then I would want you to say, stick that merit into the Kullback-Leibler divergence. And now find the distribution that's closest to that merit with no holds barred on what distribution you choose. And you would say, that's easy. If you give me a probability distribution, the distribution that's closest in Kullback-Leibler divergence is the same distribution.
Hmm.
And so you would precisely get the merit back.
All right, and just very quickly on this equation, well, in inclusion while you're here. So if I think about it as a fixed point in terms of Q star, so would it be satisfied for all the Q stars in this example, or not, or only for the Q star that's equal to the P?
So
Thanks.
I do like the thinking of fixed point. That term is going to come up in a few slides, so please hold on to that one. And the answer is it would not be satisfied by all Q stars. So if you put in, now that's a result, that's not obvious. That's something we have to show. And that's why this has content. Otherwise, we would not be doing anything useful. Put in the optimal Q star, calculate its merit, minimize, you will get the merit back and you will get that Q star back. But put in any other Q and calculate its merit, and you will get the merit back when you do this calculation, but that merit will not be the Q. That's related to the comment earlier. Generically, a distribution does not induce a merit equal to that distribution. Otherwise, we'd be in a lot of trouble.
Great, thanks a lot.
Okay,
Can I ask a question, Larry?
yeah, which, please.
In your proposition, you have script L, which refers to the constraints.
Yes.
Any limitation on the feasible constraints? Can script L be any set of distributions?
For this result, it can be any set of distributions. We're going to have a result later on where we want it to be a convex set. And well, I mean, we want the minimum to exist as well. So we'd like it to be a compact set. And the strength of that, I'll make another comment. I have described this so far as entirely a case where the returns are fixed by the technology and the planner is choosing the allocation. In the paper, we allow both the returns and the technology to be chosen by the planner. And this is a feasible set of returns cross technology. It's easier to do this, and so we focus on this case today. All right, I want to talk about the ideas behind this merit principle. And here's where I'll make my best case that there's some game theory here. So first, I want to interpret, extend is kind of a pretentious word here, the KL divergence a little more broadly. Usually it's mapping from probability distribution cross probability distribution into a number. Now I want to allow the second argument in the KL divergence just to be a non-negative function instead of a probability distribution. And so I'll talk about the KL divergence between a probability distribution and what we've called a generalized probability distribution. It has the same formula. I've just removed the bold down here. It might not, its sign can go both ways now. So we lose some of the properties of the KL divergence. We could have relaxed the candidate, the requirement that the first one be a probability distribution as well, but we will never need that. So just the one gets relaxed. This loses some properties of the divergence. As I said, we can no longer be sure what its sign is, but it retains some familiar properties. In particular, for a KL divergence, the distribution closest to a distribution P is the distribution itself. In the general case, the distribution that's closest to, let's go the other way, the distribution that's closest to a generalized distribution Q is the normalized version of that generalized distribution. Now, we're going to use that to get a lemma that uses much of the same reasoning as the Dansker-Veratham lemma from large deviations theory. And that tells us that in general, if we have a random variable from some set X in the R plus, and we want to find the growth rate associated with that random variable, it is given by this expression. It is given by the Kolbeck-Leibler divergence between the technology describing that random variable and the closest probability distribution. That's going to be our basic technical tool. To make sense of that, we need to ask what these distributions P represent and why the growth rate of this process Q is given by this consistency condition between P and Q. So now, forget about all of our previous notation. Let's just consider a growth process. So we have some random variable that is the product of some sum of outcomes. And we want the growth rate of that random variable. How do you get a growth rate? You take a log and divide by t. That's how you convert anything to a growth rate. And so we're interested in the log of the sum of q. Now, we can reformulate this. Essentially, you can sum over rows first and add over columns, or you can sum over columns first and then look at rows. To get this product T, we can think of summing within a period and taking the product across periods, or we can think of first taking the product, we can think of summing across sequences of realizations over time, and then taking the sum over sequences. So in period T, we have T periods. In each of those T periods, there's been a realization of our random variable. I can look at the sequences of realizations. That's what this is. For each of those sequences, I can take the product of those realizations. I can sum over sequences, and that's going to give me my random variable. And in addition, each of those sequences depends only on the empirical distribution of the terms in that sequence, not the order in which they arose. And so now I want to think of those sequences as playing a game with one another. I want to think of each of those sequences as being a growth process of its own, and these growth processes are contending to contribute to the growth of my random variable y. Indeed, I can think of not, since each sequence depends only on its empirical distribution P, I can think of equivalence classes of sequence. An equivalence class is a collection of sequences that have the same empirical distribution, may have realized them in different orders, but the same empirical distribution. Now, the number of sequences in an equivalence class with empirical distribution H, that turns out to be proportional to the exponent of the entropy of that sequence. That's a standard result from large deviations. And so I can write my variable that I'm keeping track of. I can sum over sequences. In each sequence, I can take how much it contributes to growth. This is the product of the random variables in that sequence. And I can multiply by the number of sequences in that equivalence class. And so I can now rewrite this. This product is just, after a little manipulation, the T times the Kullback-Leibler divergence between the random variables and the distribution of those random variables. And so now I have an object that is the sum over equivalence classes of sequences, with each equivalence class of sequence contributing this to the sum. Well, how do we think about this? This is a sum of exponentials. Each exponential has a coefficient and then scales with t. As t gets large, the only equivalence class that's going to matter is the one that has the largest sum here. Put it differently, I think of these contending equivalence classes all struggling to contribute value to my sum here, and the one that's going to win, the one whose contribution is going to swamp everything else, is the one that has the largest exponent. And so I can say that as t grows large, this variable is approximately, and this approximation gets arbitrarily sharp as t grows, equal to, well, the minimum of this Kullback-Leibler divergence. And, well, the minimum of this Kullback-Leibler divergence, that is this measure in my merit lemma. So where did the merit lemma go? I'm sorry, it's back far. This is telling us that the growth rate maximizing policy is going to be the one that minimizes the divergence. The appropriate divergence comes from this lemma. I have to make that precise yet, but that's what the argument is going to be. So going back to our questions about this growth rate lemma I had, what are these distributions that P that we're talking about? Well, each distribution corresponds to the empirical distribution of a sequence of realizations of random variables. And I can think of our original growth process being the sum of all these constituent growth processes, and the fastest growth process wins the game of contributing to this. Why is the fastest growth process the one that's consistent with Q? Two things make a growth process good. A growth process does really well if it puts high probability on values of X where the return is high. And so you might be tempted to load all of your probability on the value of X that has the highest return. In the certain world, the world I had where I had the 5 people, that would have been a good thing to do if you were allowed, if my inequality constraint hadn't prevented that. You would have put all of the probability on the person with the highest return. In general, when it's uncertain, you don't want to put all of your probability there, but you still want to put high probability on values of X with high returns. But the other thing that makes an equivalence class of sequences contribute a lot to growth is to have lots of elements in it. And what makes a sequence have lots of elements? A sequence has an equivalence class has lots of members if it's relatively random. A sequence that draws value x1 in every period has only one, or an equivalence class of sequences that put all of their probability on x1 has only one element. An equivalence class of sequences that mix half-half between x1 and x2 has many elements in it. So, with apologies for the missing backslash here, the optimal equivalence class balances. It wants to match Q closely, but wants to remain relatively random. And it turns out that the Kullback-Leibler divergence from Q balances those two forces. So that's what gives us our growth rate lemma. It tells us that any growth rate, the growth rate of anything, can be characterized by this. Now, here's the growth expression we're interested. This is the growth expression with our individuals I and our uncertain components omega. And we apply our growth rate characterization omega by omega, and we get that our growth rate, that our optimal allocation, an allocation is optimal if and only if the induced joint distribution solves this now fixed point problem. So here the fixed point actually comes back. We minimize over distribution, over these generalized distributions describing the allocation and the return. For us, the return is fixed and we're just choosing the allocation. But in the general version of this, we can choose both the return and the allocation subject to some constraints. We minimize over that and a distribution subject to the constraints that our technology has to remain feasible and our distribution has to have the right marginal. Why does it have to have the right marginal? Again, we think of this distribution as describing paths of money through the economy, and those paths are going to have to visit states in accordance with the marginals of those states. I'll amplify on that in a moment. In addition, the maximizing distribution will be the merit distribution. So this is our basic result. The earlier merit result characterization of growth is a special case of this. It follows immediately from this. A bit of interpretation of this result. These generalized distributions now, you can think of as describing a path of a dollar through the economy. The dollar starts in state one in the hands of person one, let's say, and each period it gets transferred to a new person as a result of the distribution and finds itself in a new state as a result of a new draw. And we can think of this as describing the empirical frequency of that path. And once again, each such path induces a growth rate, and the one that induces the fastest growth rate wins. And so this is just a version of the growth rate lemma. And so this is just, looking at how the clock is moving. This is just the summary of what I just said. And so the optimal policy has to solve this. I said our merit distribution policy was a special case of this. Even though we have a generalized distribution here, the chain rule for Kullback-Leibler divergence still holds. That gives me this. And now this part of the minimization problem gives me my merit principle. Fix a distribution Q, calculate its induced merit. Q, to be optimal, Q has to minimize the Kullback-Leibler divergence from that reduced merit. I've gone through that more quickly than I would have liked, but have even less time available than I would like. So I'm going to only mention now the reason why we did all this, the things that we hope this does for us. One is that following this fixed point idea, we can define an iterative process that will converge to, conceivably would calculate optimal policies for us. Fix an allocation, find its induced merit. Given that induced merit, find the closest allocation to that induced merit. Check if that allocation that we first found satisfies our, this is the closest to the induced merit. In general, the answer is going to be no, since our initial allocation was arbitrary. Iterate this process, find a new induced merit, find the closest allocation, find a new induced merit. That will converge to the growth optimal policy. This slide says roughly maximum likelihood estimation with a correctly specified model. That's a result from Hal White. Maximum likelihood estimation with an incorrectly specified model. That's a result from Burke. Can be characterized as maximizing the growth rate of a growth process. In White's case, there are no constraints on the distribution, and you end up with your estimate and the technology, the Kullback-Leibler divergence between the true distribution and your estimated distribution going to zero as you run that iterative process to infinity. In Burke's case, there are constraints on your estimate. This is the misspecification. You minimize that distance. That's the equivalent to Burke's result, that you end up with an estimate that minimizes the KL divergence to the true distribution. There's a version of this called predictive coding that first sets up what looks like an ordinary maximum likelihood problem, then says, but you know, Bayes' rule is computationally intractable. And so instead, we're going to split this into a pair of models, what they call a generative model that describes the system's prediction process, a recognition model that describes the system's interpretation of its signals. These are just equivalent to our distribution of path of money through our system and our technology. and their consistency requirements on their two models exactly match our characterization of optimal growth policies. And so we have a growth-based demonstration or replacement of the variational arguments that they use. And so we have just a complete equivalence. We can represent aggregate wealth like this. We can represent the likelihood of a sample like this. Our allocation and returns are equivalent to their generative model. Our path P is equivalent to their recognition model. And so we get the same sort of result. There's an analogy of our merit principle is this result from the predictive coding literature. As with our previous work, we have an additional interpretation or equivalence to rational inattention that I didn't put on the slides, anticipating I wouldn't get to that. And so I'll skip the summary and jump right to this empty bullet point, which I leave for your questions. And I'll go to my with apologies for the ever increasing pace, I go to my last slide. Thank you.
Thank you. If there are any questions, people, please feel free to unmute yourselves.
Just one short question. You mentioned several times the word characterization. So the only optimum policy can be of that form, right? There are no
Yes.
other optimal policies.
So indeed, that form is a necessary condition for optimal policies. It is a sufficient condition for an optimal policy if that optimal policy is interior. And if the optimal policy is not interior, we can turn that into a necessary and sufficient condition with what look like Kuhn-Tucker conditions. On this, that characterization has to hold on the support of the optimal policy, and then off the support, we have to get a characterization that looks like that but has an inequality.
Okay.
And so that's not perfectly satisfactory because that doesn't give us an algorithm for deciding what the support is, but does give us a characterization. If we know what the support is, then indeed we have an algorithm for calculating optimal policies. The iterative process that I described will do that. In that case, the optimal policy is a fixed point. The algorithm converges to a fixed point, and there are conceivably multiple fixed points in the cases where there are ties in the technology, as I will call it.
How rapidly, by the way, would the algorithm converge?
I do not have an idea of how rapidly.
Okay.
That's a good question, and there I'll betray that I think more like a game theorist who's used to equilibrium than someone who's used to convergence. I haven't thought about the speed of convergence.
Okay, thanks.
Any more questions?
A quick one.
Yeah, please.
But you ask a question, I'll ask. Maximizing growth rate is equivalent to maximizing expected utility of an agent with a utility with the logarithm form. What does it imply in your analysis? Like,
so let me first an elaboration on that. Maximizing the growth rate is equivalent to maximizing an agent who has log utility and is concerned only about wealth at some arbitrarily distant period. And so when people talk about expected utility maximization, this was a common criticism of the Kelly rule. Much of that criticism was not about the log form of utility, but the presumption that all that mattered was long-run wealth. And so the usual criticism wanted a discounted utility of the stream of wealth. If indeed all you care about is accumulation, so you're arbitrarily patient, and your utility, I see, you don't even need the log in that case. If all you're cared about is long-run wealth, then you want to maximize the growth rate. And that's an maximizing the growth rate is approximately optimal if all you care about is wealth after some finite number of periods, but not the intervening wealth. And that approximation becomes sharp as the number of periods grows. There's a sort of turnpike theorem here. Maximizing the growth rate in general does not require that you equalize wealth across agents, but it does require persistent redistribution in each period. In each period, you're taking wealth away from some and giving it to others. However, in the long run, everyone is better off under that scheme than under an autarkic scheme that would just let everyone keep their accumulated wealth. So even someone from whom wealth is constantly being extracted in every period fares better under the optimal growth scheme, given this long-run objective, than if they were just left in autarky. And the reason for that is the redistribution allows for diversification that the autarkic scheme does not.
Thank you.
More questions, anybody? Okay. And thank you again.
Well, thank you everyone for coming.
And we stop the recording.